So today I would like to talk about blackbody radiation. Now, I don't want to take the topic away from those who have chosen it, but I just would like to help them a little. And I would like to give all of you a background so that you can understand more or less what is happening. Apart from that, the reason I would like to do this is the blackbody radiation is a small problem within quantum statistics, in statistical mechanics. It's a very small problem there, which can be done exactly. And this is not so often in physics that you can do problems exactly. Very often you have to approximate them. But this one you can do exactly. And in that path to describing that, I will introduce some concepts which are important in physics generally. So what I'm going to show you is a specific presentation about blackbody radiation, which will give you concepts which you use broadly in physics. The thing I want to discuss is I have a heat bath which this is what we call an environment which is held at a specific temperature, is generally called a heat bath. Heat in French is chaleur. Is it chaleur bain, or what is the heat bath? What? Adiabatic. Adiabatic. Okay. It's okay. And now we have a smaller system. We have a system which is linked, which we can link to the heat bath. And what it means is that we give the system a fixed temperature. This has a fixed temperature T, this heat bath. And so if we join it to our system, then that system will also have this heat. Now, if this temperature is very low, then the energy, if say the temperature is 0, then the energy of the system is the lowest energy the system can be in. So we will call, for the system, we have a certain number of states it can be in. It can be in the state E0. The whole system is in the state E0. That is in the lowest state when the temperature is 0. And now if we join this to something which the heat bath is not at 0 temperature but at higher temperature. And 0 by 0, I mean, when we say that in statistical mechanics, we mean Kelvin, 0 degrees Kelvin. That's the absolute 0, and things which are at absolute 0 are in the ground state. They are not excited. They are in the ground state. And so, if we now join this, this heat bath will be the system will be in various states, depending, it's connected to the heat bath. Sometimes a little higher, sometimes a little lower, and so on, because there's exchange here. The heat is flowing in this direction and is flowing in that direction. And so the energy will not be a fixed energy. It will be a distribution of energies of this heat bath. And that distribution, we can write the probability that it will be in the state R is equal to e to the minus, and I'll use here beta R, and beta is 1 over kt, so this is ER over kt. And this is a formula by Boltzmann's formula about the distribution. I've made a mistake so far. And what is that? I must divide this by some value so that so that I choose that value in such a way that my total probability is 1 of having this thing. And so this quantity Z is then defined by this. This quantity Z is defined by this, and then this probability, if I do it this way, this probability will be, the total probability over all states will be 1. I can maybe just say a few things. This function, these energies here will depend on a number of external variables. For instance, on the volume of the system. If I make it smaller, these energies will be different than if I make it bigger, and so on. So there are external variables which influence the energy. There can be others. For instance, the number of particles and so on could be in there. Now, this quantity looks pretty useless at the moment, but it's a very essential quantity, and it has a name. It has a name. Who knows what it's called? Partition function. It's the partition function. And amazingly, that's all you need. You need to calculate the partition function. And if you can calculate the partition function, then you know about the system. So if you in German, there's another word for it, and it's sometimes used in English as well, and it says that the sum of states. The sum. What is it in French? Z, yeah. The partition. So it's also partition function, yeah. So it's a sum of all the states with the weight in which they are in that state, and so this is something which if you know that, you can calculate. You can calculate many things. For instance, let's try to calculate the average energy of this. I mean, this system here is is hopping upwards and down and so on, depending of how it interacts with the heat bath. So it's not at a fixed energy, but it has an average energy. And that average energy I want to calculate. So the way I can do it is I can take the logarithm of the partition function. The partition function is normally a very big number, and so one tends to use the logarithm of it. And I differentiate this with respect to basically 1 over the temperature, with respect to beta. Beta is 1 over kT. And if I do that, then I get, what do I get? 1 over z, and then I get d beta of z. And if I calculate that, I get minus ER, and then I get e to the minus beta ER, and I still have the sum over R here. And so this is 1 over Z times the sum over R. Well, wait a bit. I can take the Z in here again. I will not. I will take that Z away there. And I will use it with that again, and I will get PR ER. And so by doing that, by differentiating that partition function, and then maybe a minus sign, and then I must put a minus sign in front of that if I want to. So this gives me the average energy by just differentiating the partition function. And in this way, you can use the partition function for a number of things. At the moment, this still looks very limited, but depending on how we model these energies, we can do differentiations with respect to the parameters which which are in the energy itself, and then we can find, for instance, the pressure. We find the pressure by differentiating this with respect to the volume, and so on. Okay, so this is general. This is for any system. I haven't talked about black body in that respect. It's just for any system. This is the way we calculate thermodynamic quantities in something which is called the canonical ensemble. The broad theory is the theory of canonical ensembles, and this is the way and we have the partition function defined in such a way, and it gives us all the thermodynamic quantities. I have just shown how to calculate the average energy of the system, but we can calculate other properties of the system. Just speak loudly that everybody can hear you.
What happens if the system is not closed?
Not closed?
Yes.
What do you mean by that?
There are some holes.
They're holes.
Yes.
If there are some holes in the system is using energy, right?
Yes, the energy inside and outside.
Can go in. Well, then you mean there's something else here where it exchanges the energy. Then I would add that to the heat bath. I would just add it to the heat bath. I would say all the things that interact with the system I will make the heat. I will call the heat bath. Okay. If there is a system here to which it is joined, which has a higher temperature, T2, a temperature higher than that temperature, then of course we would have flow of energy from the heat bath to this system and so on. And then we would not have equilibrium statistical mechanics. Then there would, but we can with the same formalism, we can handle that. But you can see, then we would have to look at flows of energy and do calculations on that as well. At the moment, I'm looking at a quantity, a system that is in interaction with the heat bath, and it is not changing in time. Okay, it is a static system. Yes.
So is that the link of the mathematics from the system? Is just we have now a system with a lot of particles.
Yes.
And then we define the partition function. Is that a link that we can make a link?
Yes. Yes.
And if it is, why we have to take that distribution probability?
This probability distribution. Yes. That I'm afraid I have to sell you. I just have to tell you. There's simple ways of actually deriving that, but that will take me 2 lectures or so, just to derive that is the right distribution to use. And I try to sell it by telling that an important person like Boltzmann actually wrote it down. So this is something. Let us assume. What we know, what I try to explain to you is if the temperature is very low, the system will be, its full probability will be here. The P, let me draw P here, PR. Then this will be 1, and this will be 0, and this will be 0, and this will be 0, and this will be 0. This is the way 0 temperature is actually defined. Everything comes to a halt. There's no movement anymore. And now, if I increase the temperature slightly, then what will happen is that some of this probability for the system, the whole system will change, and this will be like this, and a little bit there. And if I increase the temperature more, then this will go further down, and this will be, and so eventually the distribution here will go something like this. Okay? And this is an exponential function. I just have to tell you. I can derive it for you, but I don't think we are having a course where we describe everything from its basics, but we're trying to introduce the concepts and understand them. And so I did not show you why this is exponential there. But I think it is plausible that that is a good that is a good model, and if you look in any statistical book, you will see it is being derived that that is in fact so, and it's the basis for all these statistical theories. Okay. Any other questions? Not? Now we want to, this was general, any system. And now we want to look at a specific system. And we want to look at the system of photons in a box. And photons in a box have energies which looks like this. This is a single photon, as we discussed last time. A single photon can be in all these possible states. And now we look at a general state, the energy of a general state. So I want to calculate the partition function of photons and I must write down the energy of the possible states in which the photons can be. And now you need to know one more additional thing, and that is that photons are bosons, and this is extremely important. And now I must explain to you what we mean by bosons. We can say all particles in quantum physics can be divided into two groups. And these groups are fermions and bosons. So we have fermions and bosons. And the difference between them is that fermions are exclusive, in the sense that if they already occupy a place, they don't want anybody else to occupy the place. So if they sit on a chair, they don't want someone else to sit on that chair, you know. They say, I've occupied this place and this is my place, okay? And so they are exclusive, which means that they, in each state where they can sit, there will only be one of them, either 0 or 1. There won't be more than that. And bosons, on the other hand, they are sort of more social. They say, well, you're sitting on that chair, but you could sit, someone else could sit on my lap, I don't mind, and someone else can sit on that lap, and so on, and so they can they can come together. And this is a statistical problem. I mean, it's a very interesting theory, this distinction between bosons and fermions. And it determines statistical properties of materials very, very much, whether you deal with bosons or whether you deal with with fermions. They're quite different, as you can imagine. Now, the thing is, there's a very nice link between them. I haven't talked about it yet, but these things have a spin of a half. And these things have a spin of 0 or 1. This is the spin. And again, I'm just telling you these things. I can't prove it to you. In fact, it is a postulate of quantum mechanics that this is so. And there are some people who have in the times since then and even now have been thinking about whether there are things which are somewhere in between, that they are semi-bosons and semi-fermions and so on. But the traditional theory of quantum mechanics is there are two types, and these are the two types. And so when we now look at the partition function, and we oh yes, the other thing I need to tell you about bosons is not about bosons in general, but about photons, is that their number is not fixed. If I ask you how many atoms are in this room, you may not know exactly, but we all agree this number is a fixed number. It may be so big that we don't know what it is exactly, but it's a fixed number. Or if you put in uranium-235, you want to know how many nucleons are in there. There are 235, and that number is fixed. Photons are not fixed. Photons are emitted and absorbed. And many of you have already drawn such graphs. You have said you look at state and you say, well, the excitation we had in one of the talks is here comes a photon in here, and it hits this electron and it goes up to there. And nobody has asked that person, where did the photon go after hitting that? Well, in general, if it's a photoelectric effect, it has just disappeared. So the number of photons is not fixed. And when the opposite happens, when we have a guy sitting up here and he falls down, he gets rid of the energy which is released, goes out here with the photon, and that photon comes from nothing. It just appears, and there the photon is, but the energy is given by this energy difference. So the energy is supplied, and then the photon is created from nothing. So this is a property of photons, which we can talk a lot, but I think at the moment we should accept it. And for a longer run, I can advise you to accept it. Now we're looking at these single particle states. So we want to describe a state R of the system. And the way I'm going to say it is, I'm saying, well, maybe it has N1 photons in this state, and it has the number of photons in that state is N2, This is epsilon 1, this is epsilon 2. And so the photons which I have, I'm distributing over these states. So I put N1 there and N2 there and so on. But without the restriction that they could be up at some point. If I want to put in more, then I just put in more. So there's no restriction on how I put them in. And that actually, this lack of a restriction makes this problem easy. If I wanted to do the same problem, but saying you can only go up to 1 million photons, and then you have to stop, there can't be more than that, then the problem would be much more difficult. But because we don't have that limit of how many we are putting in, the problem becomes easy. So let me, after talking a lot, just then write down the partition function. And what I have to do is I have to sum this I have to take this quantity and sum it over all possible values of n1. n1 can be 0, or it can be 1, or it can be 2, or it can be 3, or it can be 4. And so I can sum it up to n1 can be any number up to infinity. And likewise, n2 is the same, and n3 is the same. So there can be varying numbers of, I call this the occupation of that state. This is the occupation number. So this is we're doing this sum. Do you think that's an easy sum? It looks quite difficult, huh? Abstract. Do you think I get a fixed number out of that? Or I get the partition function out of it? So, you see, what I can do now is I can write this thing in a little different way. I write it as a product over R running from 1 to infinity. So that's a product over all these states. And for each of these, I write nr, and I write exponential minus beta n r epsilon r. So I claim that this thing is equal to that. So it's time to break. Won't you just take first 5 minutes or less than that, and then just convince yourself within groups that this is in fact equal to that. And if you want to, you can do it simple for yourself. You can say, well, you don't want to do it for an infinite number of these here, but you take 2 of these. You say, well, let's look at only 2 of these states, some n1 and some n2, and you write this, and then you write it as a product of 2. Or if you agree to this as it is, then you're finished, if you know that. So let's start working, and then we do a break, and then after the break somebody will explain. So speak to it. So tell them.
Where is the first one equal? What is equal to that? What is the beginning? What is the beginning?
The Z.
No, it can't be that one. Because we have
This one is it. So we can use the partition function. Yeah, this one is this expression is this one.
it's infinite.
Yeah.
It's infinite.
No, and up to the final number of particles. From the particle, this is the number of particles from 1 up to n. That's the number of particles. This is the partition function of the individual particle in a system. This is the partition function for molecule 1. This is the partition function for molecule 2. Up to the partition function of the final molecule, what you have. This is the same as before. This is the same as it's similar.
Someone else. Come, someone else. You go. Ah.
The first thing is the summation continuous. Okay. So that's the first. That summation is continuous. Okay. So that's the first. So you take 1. Start from 1, 7. Yeah.
This is similar to this one.
No,
No, it's not the same.
no, it's not the same. You see, you
now
can't.
you have to increase like.
So you continue some business. So this is modification. So we can say infinity for modification, and then we take 1.
There's a sum there.
Similar. This is the same.
Yeah, some. This is for the modifications. This one. And this one. Take on this one.
Okay. Let's just make sure that this attempt is not right, because I run in this brackets. I run n1, n2, n3, n4, and you say I multiply it to the power n. But n1 is not a fixed thing here. It's It's been running through all values from 0 to infinity. And also, when I make a sum and I make it to the power of n, then I have cross terms. You what?
That is correct. I want to write it clear.
Is it proof?
Very clear.
You want it clear? Come here. There's a part of the board, and you write it clear.
Il a commencé par où?
I can finalize this version in the final partition function.
That is the final function. Yeah.
So,
Yeah.
but can we find the value of this expression? Just to find the other expression.
Yes.
The meaning.
Yes. Yes, we can do that. Yeah. No. Is that n? Oh, you start from 0, n0. Yeah, but I think it's the same as this. Yeah. Yeah, okay. Everybody understood? Huh? So this we could do because all these sums were independent. And if they had been dependent, then we would have to worry about in between that the sum up to n1 plus n2 is some value which we have to, and gives a restriction, no? And that's more complicated. Another comment someone made said there was no chemical potential in this thing, and there should be a chemical potential. And this has exactly to do with the same point. If you put in, for those who know statistical mechanics, if you have a chemical potential in there, that is actually a way of fixing the number of particles in a different way, that you have open sums and you put in a chemical potential which restricts the system. We don't have it here, but I just wanted to comment on why it's not here. It's because these photons are not restricted. There's not a fixed number. Oh, here, I took this thing out. Oh, sorry. Okay, so this is the partition function. And this thing goes from 0 to infinity, and this goes from 1 to also infinity. And so this R runs over these different values here. For that specific state R, it runs over all these values, and n of R runs over these values of n. How many we have in each of them. Now, if we calculate the log of the partition function, then what do I get? Maybe I should do something else before we do this, but you can think about what happens. And that is, can we do this sum? You can do it. You can do it. You want to write it down? Okay, write it down. Come here. Yeah. Yeah, but I think we want to do what you do is correct, but it's not the same. We look at this as a different way. What is this sum?
Like this is a no the
Geometric.
geometric suite.
Yeah. Okay. So what's the answer?
You have, for example, this carré, this cube.
Yeah. Yeah. 3 and 4 and so is enough now. Okay.
This is a 1 sur 1 is
Okay.
infinity. So you have this. The first term of this is a 1.
Yeah.
1. So you have 1, 1, 2. Huh? The reason. Reason. Yes, is
I think you must just write down this thing.
Yes.
Don't write this down. Just write that.
Okay. The first term is
P to epsilon r to the power n r.
okay. Un moins.
Peut-être que tu dois epsilon de R, quoi.
Exponence.
Is epsilon the same epsilon 1 is equal to epsilon 2?
Non,
R.
epsilon 1
Epsilon de R.
Ah, this is not the sum of r. This is the sum of
Epsilon R. Epsilon.
nr. This energy is given by that product. Eh?
Correct.
We set it there and then. Okay. C'est bon. Okay, thank you. Okay, so this terrible sum now looks much easier, and so now it's a good time to calculate log of z. So what is that? So it's sum over r of the log, well, you can put in a minus sign maybe, 1 minus e to the minus beta epsilon r. So we've calculated that. And we are basically, have I done it correctly? Yeah. Okay. Now if I go back to this quantity here, and I want to know what is the average number of states in the average number of occupation, the average occupation of this state. So I want to say what is the average number of N3. So how can I do that? I differentiate this expression, the log of this expression, I differentiate with respect to epsilon 3, and then I get an N3 down, just the same way we did it here. And then I get this epsilon 3 down with this expression, and so that gives me the average number. Is it clear? I take the log of this, and then like I did there, and so I just leave it as it is, but I take the log of it, and then I differentiate d epsilon 3 log of z. And so if I do this differentiation here, first of all, log of z gives me 1 over z, and then I must differentiate the log. And so if I differentiate it with respect to epsilon 3, I get here n3, and still the sum of all the n's, and then again this exponential function which I have here, minus beta, and so on. And this 1 over nz times of this gives me the probability that it is in state 3, and so it's what it gives me is the probability that it is in state 3 and times epsilon 3 times n3, because I differentiate it with respect to epsilon, I get n3, and I have to sum over all the let me see now. So I've got a little bit my space problem here. I will not, let me write it over, but I'll write it in so that it's not as confusing as it is over there. So I've got all these sums, And one of the sums is sum over n3. But there are many others as well. And I have exponential minus beta, and then all these quantities, and one of the quantities is n3 epsilon 3. And I calculate now the differential of this, which will give me 1 over z, the log of this. I take the log of this, and if I differentiate the log, I get 1 over z, and then the differential of z again. No? So with whatever I differentiate. And so it's 1 over z, and if I differentiate this with respect to epsilon 3, I get n3. That's a number. The number of photons in that state, and then this exponential with all the weight of all these things. And here the sum of all these things. Huh? And so this will say this is equal to the expectation value of n3. Well, this is n3 times the probability that I have the state 3. So this will give me the expectation value of n3. So remember how we calculate expectation values. We do it this way. We get the value, and we write it this way, and then we get the expectation value of that value, which came down when we differentiated. And here we have the same thing. We have the full probability here, and there's an n3 in here. So I can write that as n3 times the probability 3, and then I sum over all these things, over everything, with 1 over z. And so I have a probability that it is in n3 times n3, and I sum over all these, and that gives me the average probability of that. Okay? Over? Z gives us the sum over everything. And here I also sum over everything. And the sum over everything is like here. It's a sum over R. It's a sum over everything. And then the value of this one thing, and then I have the probability of that one thing which I put.
This formula and the first formula here is the same. This probability. Last one.
This one?
Yes.
Yes.
P3.
P3. There's no Z here, yeah? P3, yeah. The Z is necessary to make all this P again, huh? A probability again. So it's it's the probability to have n3 summed over all the space, the whole spaces. And that's what such a thing is. It's a value times the probability summed over all states. Is it correct what I do? I think you must write it out, and if you have problems with it, and then we can talk about it again. So what I actually want to do is I want to apply this to this formula. I was just trying to show you that in order to find the probability of a photon in the state nr, I have to take this function and differentiate it with respect to epsilon r. That's what we did there in the original function, but now we've written it in a different form, and the result is still the same, that if we differentiate it now here, we get what someone said, -1. If I differentiate this, I get -1 over beta, and then I have to find d epsilon r of log z. No, sorry, okay, and if I differentiate that, I get 1 over 1 minus e minus beta epsilon r. So this is I've made a sign mistake and a beta mistake. Here already I made a mistake. When I differentiate that, I don't just get n3, I get actually beta times n3. Minus beta, so this result wasn't quite correct. And that beta is haunting me now because I get it again. And so this is why I have it this way. But the sum total of what I'm trying to do here and we maybe need to look at it a little more carefully again, is that the average number of photons in any specific position r is I also have a sign for a mistake somewhere. If someone picks it up, please tell me where it is. So this is the end result. This is the occupation of various states. And now if we want to know what is the energy in any specific interval, we have to take that occupation and multiply it by the energy of that interval. So what I have to know the occupation, which is this, times the energy, and that gives me the amount of energy that sits in this interval here. And if we translate that to the photon energy as such, we say we want to know what is the energy of the photon gas in between omega and omega plus d omega. In this interval, we want to know what is the energy of the photon gas in that. So what we have to do is we have to take the occupation, which is 1 over exponential that must surely be minus beta. Huh? Is that right? Plus beta? No, it's actually plus beta. That's the occupation. And now we want to know how many states are there at this level between omega and omega plus d omega. And that we calculated last time. We counted the number of states. Because at this interval, there's not only one state, but there are many states here. And each of these states, we want to know how many are in this interval, certain interval here, d omega. And so we have to multiply this thing by the number of states, which is, I don't remember it offhand, but we did calculate it. The number of states, so we have to multiply this by the number of states, which is f omega d omega. So we know how much what is the occupation of each state. We have to multiply it by the number of states, that is v omega squared d omega over pi squared c squared. And now we have to multiply that by the energy of that. So this is the occupation of any state, any possible state. This is the number of states we have in the interval d omega. And for each of these many states, we have the energy h bar omega, which is the photon's energy in that interval. Yes?
In the exponent should be negative or
What should be negative?
because the exponent is minus beta.
Is this minus?
Yeah, so it should be minus, yes? It should be less than 1.
I think it's positive. Huh? I think we haven't followed it through very nicely, but
exponential means beta epsilon L in the overall function.
come please show me. I've lost a little bit of control of everything, so that's right. Yeah. So and then you divide by this, and then this comes in. Yeah. Sorry, there were too many things happening at the same time. Now this thing we call if we divide by V, V is the size of the system, the size of our black body. So if I divide by V here, then I get the density of energy, energy density, energy per unit volume. And I will call that U, and it depends on the temperature, and it depends on omega. And that is given then by, as we have it there, h bar omega to the third, and then this exponential beta h bar omega minus 1, and then there's still here pi squared over c squared. Is it c squared or c to the third? C to the third, yeah. Okay. C to the third. And then in both cases, I could write d omega. That's the amount of energy in an interval d omega. But I can leave it away. I just want to see this function here. And if you draw this function, then it looks something like this. Depending only on, now this is, I draw it as a function of omega. And this is this intensity U, the amount of energy. And it depends, this function depends on, only on T. And this is actually a wonderful result. We normally don't get such easy results in physics. It's a wonderful result. You calculate this, and independent of everything else, you get a result. The amount of number of photons, the photon density, is only dependent on T. And it's an exact result, and it is a result which we use when we look at the radiation from the sun or from any hot body. And so there are a couple of little things. I want to stop now, but there are a couple of little things you can check for yourself, and that is just find out what is the value of that maximum. Well, where is the maximum? And I can give you an answer, but you should check that yourself. So all you do is you differentiate this with respect to time, to temperature, and you find the maximum. You set it to 0, and then you get this expression, which actually, if you have the maximum, you can calculate what the position of the maximum. You can calculate what the temperature is. So if you could look at a curve like that, you can look at the maximum, and from that you can immediately say what is the temperature of the body. And this is in fact the way the temperature of stars and we determine the temperature of the sun and so on by just looking at where is this maximum of its spectrum. So you can measure the spectrum and do that. The other interesting little thing which you can also do, and I would actually advise you to do that, is to take this function u t omega, and you integrate it over all omega. So the integral over this here, that you can easily do. I mean, you just change the variables, and so that you get a nice integral and thing you can integrate. And what you then find is that this goes like a quantity A, which is a constant. We have an expression where you can calculate the expression for it, times t to the fourth. And so if you measure the total heat coming from a black body, it will, as it changes with temperature, as the total heat that comes from it, from that you can also determine the temperature. And you can see if the sun, which is fairly hot, it gives a lot of energy out, and things which are cool give much less energy, total energy in the shining. Yeah? So if you do this integral, which I said it would be nice if you could do it, then I can just tell you what A is. A is equal to pi. I mean, it's just a quantity. It's just a times k to the fourth. That k is Boltzmann's constant, because if it's t to the 4, there must be a k to the 4 in it as well, and then it is divided by 15 times h bar to the third 3 c squared, c cubed. And you see, interestingly enough, here again we have h bar, which is our reminder that we did all this in quantum mechanics, and you in fact need quantum mechanics to do this, because otherwise you would not know what that constant is. Before there was quantum mechanics, before Planck did their work, people didn't know what this. They already knew this, that it goes like t to the 4, but they didn't know what the constant was, and in fact that constant contains Planck's constant, and the only little extra I could give you here is that if you do this stuff, and you will get up to an integral which looks like this. And that integral, maybe you can find it quickly yourself, but I can't, so I had to look it up, and that is the value of that integral. So if you integrate it, so if you are left with an integral, and then that if you put in that value of that integral, then this is the value of A you get, and the total energy which is in the system goes like t to the fourth. I hope this is a bit of a messy thing to do all this stuff, and I can assure you that if you do another problem other than the photon gas, it becomes much more messy. Huh? It really becomes messy, because then you have all sorts of restrictions you have to worry about, and so on. So this is actually the simplest problem you can do in statistical mechanics, and you can do right from scratch. You could understand every step, I hope, and if you don't understand it, please come and see me, and I will explain it to you once again. And now, bon weekend.
How do you see?